What's up, AP Physics people? Today we are going to be learning about momentum. Now, what is momentum? Momentum is best described as a measure of an object's motion. We use the equation P equals mv, where P equals momentum, m equals mass, and v equals velocity. Now, what does this equation tell us? The more mass an object has, the more momentum it has. The more velocity an object has, the more momentum it has. The unit for momentum is kilograms times meters per second. Since momentum is a product of scalar quantity, mass, and a vector quantity, velocity, momentum has a magnitude and direction. So when you're writing your answer out for momentum, do not forget to add the direction in which momentum is moving. Let us try a very simple sample problem. A car that weighs 1,000 kilograms is traveling at 100 kilometers per hour to the right. What is the momentum of the car? Well, we have our mass, 1,000 kilograms, and we have our velocity, which is 100 kilometers per hour. However, we need to convert kilometers per hour to meters per second. Rounding to the nearest tenth, our speed should be 27.8 meters per second. When we multiply our mass, 1,000 kilograms, times 27.8 meters per second, which is our velocity, our momentum should be 27,800 kilograms times meters per second. Now, since the car is moving to the right, we have to add the vector to the answer. So let's not forget that. And there we go. We solved our first momentum problem. It seemed pretty easy, but momentum can get really hard. Now, let's look at collision. Collision can be best described when an object in motion hits another object. Just how like we have laws conserving energy and mass, momentum is something that is conserved. However, this can take different directions. Let's look at the two types of collision, elastic and inelastic. Elastic collisions are when objects that hit each other remain separate after the collision. In an elastic collision, kinetic energy and momentum are conserved. This is really important to remember. A good real-life example of an elastic collision would be billiard balls. Let's watch the video to see how these billiard balls interact with
the cue ball off the table.
When the balls collide with each other, they remain separate. Hence, they are an elastic collision. Here, the kinetic energy and momentum are conserved. Always keep that in mind. All elastic collisions conserve kinetic energy and momentum. When we are calculating elastic collisions, we often approximate collisions as being elastic. For example, energy conservation is not perfect when someone spikes a volleyball because there is sound that is released as energy. Now, let's look at the other type of collision, an inelastic collision. In an inelastic collision, the objects become one mass when they collide. In this situation, total momentum is conserved, but kinetic energy is not conserved. That is the big difference between an inelastic collision and an elastic collision. In an inelastic collision, most of the energy will turn into heat or sound. A good example would be two separate train carts that couple together when they touch. Let's look at a sample AP problem. A 50 kilogram skater at rest on a frictionless rink throws a 2 kilogram ball, giving the ball a velocity of 10 meters per second. What is the momentum of the skater after he throws the ball? Well, let's look at our system before and after the skater throws the ball. Before he throws the ball, he is holding it. Therefore, the total mass of the system is 52 kilograms. He is not moving, so the momentum would be 0. After he throws the ball, there are two objects in the system, the skater and the ball. We can calculate the momentum of the ball by multiplying the mass and the velocity, which would equal 20. We also know that the skater weighs 50 kilograms, so all we need to do is solve for his velocity. At the end, we get negative 0.4, which would be the momentum of the skater. Now, let's take a look at impulse. In order to find the change of momentum in a system, we use impulse. The equation for impulse would be delta p force times delta t. This can be rewritten as F delta t equals to mass times final velocity minus mass times initial velocity. Newton seconds would be our units here. What this shows us is that when time is increased, the momentum of an object decreases. This is why airbags help reduce our momentum as it slows down the time of the collision. Let's watch a video that compares two car crashes. One where the test dummy has his airbag deployed, and one where his airbag is not deployed. As you can see, the dummy's momentum is significantly decreased when the airbag is deployed. Since we didn't talk too much about graphs in class, let's do that now. Graphs of force versus time can easily help us calculate impulse. All we have to do is find the area under a force versus time graph. If it is constant, all we have to do is calculate the area of the rectangle. If the force is constantly changing, however, then we would have to find the area of a triangle using 1/2 times base times height. If you see a bell curve shaped graph on the AP exam, do not worry, because they will only ask you to approximate the area underneath the bell curve. It does not have to be perfect. Alrighty, that pretty much wraps it up for momentum and impulse. If you have any questions, leave some comments down below. Don't forget to subscribe, and next time, we will be talking about whatever Mr. DePaulo assigns us next year. Thank you.